Hi, in this video, I'm going to give a quick introduction to Lagrangian mechanics. Now, this is going to be a framework that we can use to study classical physics systems, which is different from the one that you learned in your introductory physics classes. So, more specifically, in intro physics, where you were studying again systems in classical mechanics, so we're studying balls rolling down hills, pulleys, things like that. You analyzed these systems by enforcing Newton's laws, right? You used F equals ma specifically. And we used forces in order to determine equations of motion, which then we could solve to find particular motions of a system given some initial conditions. So forces lead to equations of motion to find the behavior of our system. So that's probably how you've thought about physics for most of your physics career, maybe up until now. When you learn about Lagrangian mechanics, we're going to be doing this, well, we're going to be studying the exact same types of systems, and the answers that we will get will be exactly the same that you would have gotten if you used Newton's laws, but the framework that we're going to be using, so what we're actually going to be doing is going to look very different. So instead of Newton's laws, we're going to have the Euler-Lagrange equations. We are not going to be thinking about forces at all. And instead, we're going to be thinking about energy. So we'll be thinking about the energy of our system and the potential energies that are involved in our system are going to be much more foundational to telling us what system we're thinking about. So we're going to focus on energy. And something known as Hamilton's principle, or the principle of least action is going to be underlying everything. That's sort of going to be our key axiom in Lagrangian mechanics. And we're going to have an object known as a Lagrangian, which is going to sort of be the defining object for our system. So whereas before when I said, oh, you have this system, it's a ball rolling down a hill. The hill is going to provide some normal force. There's going to be gravity that's pulling it down. Do we have friction or maybe we don't have friction? I'm giving you these forces and you're going to then apply Newton's laws to find the equation of motion. In Lagrangian mechanics, instead of giving you this list of forces which define the behavior of our system, I'm going to give you this object, which will be called the Lagrangian. And that's going to sort of define the particular system that we're dealing with. And then we're going to plug this into something known as the Euler-Lagrange equations to find our equations of motion. So these Euler-Lagrange equations lead to our equations of motion. So EL here is Euler-Lagrange equations. And those equations, the key thing is everything is going to look very different if you study a classical mechanical system in this way, up until this point, which is the point of the equations of motion. So once you find the equations of motion, you'll find that these two very different methods will agree. Now, Lagrangian mechanics is going to feel like we're really overcomplicating things. Like, why are we reinventing the wheel here? Why are we doing this in this different way that feels mathematically more challenging? Well, Lagrangian mechanics ends up, for complicated systems, ends up being a lot nicer mathematically. It actually is a lot easier when the more complicated your system is, the easier it is to solve using Lagrangian mechanics. So if you just were studying classical mechanics systems, that would be the reason. For the purposes of particle physics, ultimately we're going to, this object known as the Lagrangian is going to be very key in studying particle physics. And we're going to be using Lagrangians all of the time. And so it's important in a particle physics class to have at least a little background in Lagrangian mechanics so that this object, this Lagrangian that we're going to be dealing with, is familiar. Otherwise, you don't actually need to be an expert in solving the Euler-Lagrange equations in order to do particle physics. It just is going to help us to see where things in particle physics are coming from. Because ultimately, again, everything we're doing here is classical. When we do particle physics, we're going to be studying quantum theory. So we're going to really be taking it up a notch. And just having this underlying classical knowledge in the background is going to better help you understand what we're doing when we're studying these quantum field theories. Okay, so that's a little bit of an overview. So I keep mentioning this object called the Lagrangian. So let's talk about this. So this is a scalar field. Or in field theory, I guess it's a scalar field. It's a scalar object, I guess I should say more generally. That usually can be computed very simply by the kinetic energy minus the potential energy of your system. This is specifically for conservative systems. But there are other ways of determining this object called the Lagrangian for other systems. But that's sort of beyond the scope of what we need for a particle physics class. All right, so in general, we can think of our Lagrangian as being something like kinetic energy minus potential energy. So this is where I'm saying instead of thinking about our physical system in terms of forces, we're going to think about it in terms of energies, and then we're going to write this object called the Lagrangian. So we say, oh, we have this ball, and the ball is moving, so it has some kinetic energy, 1/2 mv squared. And additionally, I'm going to attach the ball to a spring, so it's going to have some harmonic oscillator potential energy associated with it. And that's our potential energy. So we can write those things down, and that is going to sort of define the system that we're dealing with. Is the ball just attached to one spring and it's vibrating and then it has some potential energy associated with that? Are there two springs maybe? Is there also gravitational potential energy? So we think about all of these energies and then we can write this thing down called a Lagrangian. And we think of that as sort of defining what system are we dealing with? What physical system are we dealing with? And then the underlying physical law that we think of is Hamilton's principle, which tells us if we compute something known as the action, we use the letter S always for the action, which I'm sure there's some good historical reason for S, but I don't know what it is. This is the integral of our Lagrangian with respect to time. And this action is known as a functional, and the equations of motion for our system are found by extremizing the action, right? Extremizing meaning, just like in calculus, right, finding maximum and minimum points. So this action is this quantity that we could compute if we have our Lagrangian. And we want to find the action that is maximized or minimized, which seems like a hard problem. Fortunately, this is a problem that's already been solved. It's from the calculus of variations is the field of mathematics that already solved exactly this type of problem. And the solution comes in the form of the Euler-Lagrange equations. So the solutions of these equations will extremize the action and therefore lead to our equations of motion. There are derivations of the Euler-Lagrange equations that are not too challenging. I'm not going to go over them in this video, but you can just look it up and find them. Here, I'm just going to give you the answer. So our Lagrangian, of course, it's going to be a function of our coordinates. So if we just have a ball moving in one dimension, it's going to be some function of the position of that ball and the speed of that ball, right? We know the speed will come up in the kinetic energy, and then in the position, maybe there's gravitational potential energy, so we care about the height of the ball or something. So our Lagrangian is a function of our coordinates, and we might have many coordinates, and it's standard to use Q to represent, they actually call these generalized coordinates. And Q dot, the thing I wrote down, is the dot here is a common notation for the time derivative. So if we're considering, for instance, x just being our position, then x could be our generalized coordinate, and x dot is the velocity. It's the time derivative of x. And Q is just the letter that's used often to represent our coordinate. And we use Q because we don't want to constrain ourselves to just X, Y, and Z Cartesian coordinates. We might be using angles. Often in classical mechanics, you define all sorts of weird coordinates. And so we use Q because it can represent any type of coordinate, whether it's Cartesian or polar or something weirder. We want to allow for all of it. And so Q is just representing some coordinate telling us about the configuration of our system. And our Lagrangian is going to depend on the configuration of our system. It's going to be a functions of our coordinates and our sort of velocities, our Q dots. And so if we take these partial derivatives of our Lagrangian with respect to our coordinates and our Q dots and plug them into this equation, then that's going to lead to our equations of motion. I'll mention there, generally for a three-dimensional system, for instance, you're going to have multiple coordinates. So it's important to note that there's an equation that looks like this one. So there's one of these for each generalized coordinate. So that might just be you have a ball in three-dimensional space that's moving around, and so there's an x, y, and a z coordinate. And then you would have one of these equations for each x, y, and z coordinate. And so you get one equation of motion per coordinate. One thing that's important to note when you solve this is that when you take these partial derivatives, you treat q and q dot as totally independent. right? When you take partial derivatives of some multivariable function, you, if we're taking the derivative with respect to x, you differentiate with respect to x and keep all of your other variables, you treat them as constants. That's what you do when you take a partial derivative. And what I'm telling you is if I'm taking the partial derivative with respect to x, and there's an x dot in my function, you might be inclined to think, oh, am I doing like, do I need these things seem related? So do I hold x dot constant? And what do I do with x dot? Well, I'm telling you in the Euler-Lagrange equations, you are told that we are treating x and x dot as totally independent. So you hold x dot, you treat it as a constant if we're taking the derivative with respect to x, for instance. And so we're going to treat our q's, our coordinates, and the q dots as totally independent when taking these partial derivatives. Okay, to better understand this, I think you need to go through some examples really in detail to get a grasp of these equations. But at the end of the day, again, in order to make progress in this class in particle physics, you don't really need to be an expert in doing these things. It's just good to sort of have it in the back of your mind that there's this whole other way of doing classical mechanics that involves this object called a Lagrangian. And importantly, this Lagrangian can be thought of as the kinetic energy minus the potential energy of your system. And understanding that this Lagrangian is sort of defining what physical system that you have. Those are sort of the main things that you need to take away, whether you are expert in actually solving these things for classical mechanics systems or not. Uh, it's sort of okay if you're not. All right, so that is Lagrangian mechanics in a nutshell.